I've always done things kind of differently, which is kind of okay. I always knew I was a little bit different from everybody else, but I embraced that. And so that kind of goes along the lines with what I get to do now as a woman in science. I get to be Miss America, but would you believe me if I told you that science is what helped me become Miss America? Does that make any sense?
Yes, very much so.
Oh, good answer. So I did a science demo at Miss America, and we're gonna replicate that today. Have you guys ever seen Elephant's toothpaste before? Have you seen it? Yeah, some of you have seen it. And for those of you who haven't, let me just tell you, you cannot brush your elephant's teeth with this. It won't be good for their teeth. When you pour hydrogen peroxide on a cut or a wound, it bubbles. And that is because of some really special properties of hydrogen peroxide. In hydrogen peroxide, there's 2 hydrogens and 2 oxygens, so it's H2O2. Well, water's pretty neutral. It's around us all the time. It's pretty stable, so when this breaks down, it's like, heck, I'll just be some water. And then I'll release some oxygen. I break off an oxygen, that bubbles out, and we're left with water. So, first thing that we're gonna do is we're gonna use a different type of hydrogen peroxide. I'm gonna give this to Miss Audrey. This is 35% hydrogen peroxide. This is 3% hydrogen peroxide, which basically means in every amount of liquid, there is almost 12 times more molecules of hydrogen peroxide in this bottle than in this bottle. And so she's gonna measure 20 milliliters of hydrogen peroxide and put it in that graduated cylinder. So I mentioned the bubbles that happen when you pour hydrogen peroxide on your skin. Hydrogen peroxide is not something that we want just floating around our body. It's not good for us. And so our body has a great way of getting rid of it and breaking it down. That's called a biological catalyst. And this reaction, when we do it, is called the catalytic decomposition of hydrogen peroxide. So we are going to use a chemical catalyst rather than a biological catalyst. And we have that right here. It is called potassium iodide. And that is what we're going to use to break down the hydrogen peroxide. And so we know that we're going to be left with water and the oxygen gas. You guys ever done the dishes? So if we add a little bit of this dish soap into the hydrogen peroxide, you're gonna get the bubbles. Another really important component called food coloring. Okay, and then I'm gonna have Audrey shake that up for us. Perfect, get it all well mixed. And now we are going to pour our chemical catalyst in there. Should we count down? Maybe count from 5, 4, 3, 2, 1, pour it. Okay, give it a second. Woo! Okay, now watch. It's a little hard to see, but when I put my hand over this, there's heat coming off of this. That makes it an exothermic reaction. So when chemical bonds are created or broken, there's a release of energy, and oftentimes that's released in the form of heat. This was really, really cool, but there's a couple other ways that we can do Elephant's toothpaste. So I'm gonna have Miss Audrey grab 2 different pieces of glassware, and the thing is, we're gonna do this reaction again with the same amount in both of these, and we're gonna watch what happens differently. And the question that I wanna ask you before we start is, which one of these do you think will shoot the foam higher, and why? So we're gonna put the same amount of hydrogen peroxide in each of these, and then we're gonna put a cap full of dish soap in each of them. It doesn't matter necessarily how much of each thing I put in, as long as I put the same amount in each one. Yep. One of the reasons that a scientist might choose to use something like this versus something like this is because you can swirl your chemicals around without it splashing. So we are now going to use our catalyst, and I think we decided we were going to use 20 milliliters. That's what we did last time. Cool. Okay, cool. It's coming up. Ooh, kind of just poured right off. Now, that one didn't shoot as high, but I can see it's coming out faster.
Yes.
Okay, ooh, that's kind of cool. Oh, that's really kind of cool. Kind of looks like a worm. Okay.
Wait for it. Wow.
So, it's a little hard to see with these because the catalyst isn't as strong as before, but the real answer is this one is always going to shoot higher, the shorter one. And it's not because it's shorter. It's because of the shape. The way that this Erlenmeyer flask is shaped, it has a big bottom and it has a skinny top. you give it less space to come out of, and it makes it shoot farther because you're building up pressure. And that's what happens with this shape. Versus this one, you can't really build up pressure the same way because it's skinny the whole way. This one definitely had a little bit of a higher lift, built up some more pressure, and that gives us some knowledge of not only how the reaction works, now we kind of figured that out, but now how we can use this reaction to change the outcome, right? We can use two different pieces of glassware and make it look a little bit different. And that's kind of what you do in the lab.
It takes a lot of trial and error. And the important thing is error. They call it trial and error because it doesn't always work.
Absolutely. I think that that's such an important thing to know because none of us like getting things wrong, but that's part of what makes science really cool because we get things wrong and then we figure out a different way to solve that problem. And so when you go through your science classes, I want you to be okay when you get things wrong, and then you learn from those and you do it differently the next time because that's exactly what the scientific process really looks like.